Hey, welcome back to our notes from Unit 8, Lesson 1. We're looking at example 2, where we want to look at limits and how they relate to the formal definition of a continuous function. So earlier in the year, when we studied parent graphs of functions and we looked at the difference between a continuous and a discontinuous function, we talked about whether we could trace the function's graph with our pencil without having to lift the pencil. So there couldn't be any holes in the graph or breaks due to an asymptote or jumps. For example, in a piecewise function, those would be things that would cause a function to be discontinuous. So now that we have looked at limits, we can examine the formal definition for a continuous function, and that states that a function f of x is continuous at x equals a if and only if, that's what the IFF means, if and only if, three things are true. First, f of a has to be defined. There has to be an actual value. Then secondly, the limit from the left side approaching a has to equal the limit on the right side approaching a. And thirdly, that limit has to be equal to our function evaluated at a. So you can see how all three of these are all kind of intertwined in a continuous function. So in this example, we're going to let f be this piecewise function. It has, for x's that are less than or equal to 0, a subfunction 1 minus 4 cosine of x. For x's that are strictly greater than 0, the subfunction is quadratic. It's x squared minus 5x minus 2. We're asked, is f continuous at x equals 0? And we want to justify our answer using this formal definition. So we need to check that all three of these things are true. If any one of them is false, then this would not be a continuous function. So we're going to start by examining f of a and seeing if that is defined. A is 0 because we're checking to see if f is continuous at x equals 0. And that means we want to check our piecewise function to see where 0 is defined. Since the first subfunction, 1 minus 4 cosine of x, is defined for x's that are less than or equal to 0, that's the one we're going to use. And we're going to substitute 0 for x and then evaluate. So the cosine of 0 is 1. We learned that in our last 3 units in trigonometry. And 1 minus 4 times 1 is negative 3. Negative 3 is a real number, so f of a is defined, and we've satisfied the first condition in our definition for a continuous function at x equals a. Okay, next we want to see if the left-sided limit is equal to the right-sided limit. Okay, our left-sided limit is the limit as x approaches 0 coming from the left, so we have a little minus as our superscript. That's on the function f of x. So as x approaches 0 coming from the left, right, that's going to be less than or equal to 0. So again, we would be using our first subfunction, 1 minus 4 cosine of x. We substitute in the a, which is 0, and that's going to equal negative 3. So from the left side, our function is equal to the function evaluated at 0. Now we need to check the limit from the right side. So now we want to examine the limit as x approaches 0 coming from the right for the function f of x. And those would be x's that were greater than 0. So now we're on the quadratic subfunction, and we're going to substitute 0 for each of the x's. So 0 squared minus 5 times 0 minus 2, which is negative 2. And that's a problem, right? Because our right-sided limit does not equal our left-sided limit. And that was a requirement for a function to be continuous at x equals 0. So this is not continuous at x equals 0. Okay, now in B, we want to let f be a function defined by f of x equals 6 plus 3x for x's that are strictly less than 1, or 9 plus 2 natural log of x for x's that are greater than or equal to 1. And we want to decide, is f continuous at x equals 1? And justify your answer using the formal definition of continuity. So go ahead and pause the video, give this one a try on your own, and then you can resume when you're ready to go over your answer together.